Okay, so I'm looking here at the thermal equilibrium diagrams for Leaving Cert Engineering and how to draw them. Okay, so first thing to note is there are three main types of thermal equilibrium diagrams we look at in Leaving Cert Engineering. Okay, so the first one being our solid solution ally thermal equilibrium diagram. The next one being our eutectic diagram, and the final one being a partial solubility thermal equilibrium diagram. Okay, now for this example here, I'm going to do a eutectic thermal equilibrium diagram. Okay, so this is the 2019 higher level question 4 part B. Okay, so the first thing is drawing these diagrams. A lot of them is the same. Okay, so there's a lot of marks going for. There's generally 10 marks out of 50. So if one of these questions worth 50 marks, generally you get 10 marks for drawing the diagrams. Okay, so it's almost for 20% of the question, and it's a 20%. It's very achievable to get. Now, so the first thing I want to look at is actually drawing the diagram. Okay, or the graph. Sorry, or the diagram. Yeah, thermal equilibrium diagram. Now, in this diagram, it says the table shows the solidification temperatures for various alloys of cadmium and bismuth. Okay, so we always know that when we're talking about eutectic alloys, two metals we're looking at are cadmium and bismuth. Okay, because it's at a very low melting point. Okay, so the first thing is looking at the percent of cadmium in the alloy. Okay, so the top section, so the percent of cadmium in the alloy, this is always going to lie along my x-axis. Okay, so this is my x-axis here coming along. I want to spread this out as much as I can. Okay, so I need to go from 0 to 100 across my x-axis. This is my starting point here. Obviously, this here is going to be 0. Okay, I'm going to come over in boxes, depending on the graph paper. I'm going to go 20. So I'll just zoom into that. 20, 40, 60, 80, and 100. Okay, each individual, and then in between is going to be 10, 30, 50, 70, 90. Okay, so this is the important thing in this here. Always label your axis as well. So this is percent metal in this case. Okay, and this is going along my x-axis. It's very important to make sure that the distances between each of my values is the same. So I've used 1, 2, 3, 4, 5 little boxes between it to get to 10. Okay, so each of these little boxes represent 2%. So that's the bottom part done. Now the next bit is the drawing is the start and end of solidification. Okay, so the unit we're looking at here is the degrees Celsius. Okay, so the unit we're looking at basically is temperature. Okay, so just putting temperature in here, put the unit as degrees Celsius. Okay, so I'm just going to turn it around like that. Okay, so we see here I'm after putting it in. Now, I want to spread this out as much as I can along this graph to make it nice and big, so that it's very easy to read different values and be able to understand it, rather than try to compact it in small. The main thing is that, again, that the distance between all our values are the same, and so on. So we need to decide how far we're going to come between with each value. Okay, so I see the highest value on this graph is 321 degrees Celsius. That's the max point I need to get to on my graph. So what I'm going to do is I'm going to come up here in intervals of 50. So each of these boxes are going to represent 50 degrees Celsius. 100. Okay. I'll stop at 400. Okay, the reason I'm stopping at 400, I actually could have stopped at 350 if I wanted to, because we know that the highest value is 321, so I don't have to go any higher than that in my graph. Okay, so that's my axis. That's all my graph and axis set up. Okay. Now, so the next part of this graph is actually just plotting the different points. And what I would advise you, if you're doing this part in pen, that's fine. What I would advise is do the rest of this part drawing the graph in pencil, okay? Because it's easy to make mistakes in the graph. So the first thing we're looking at in this is we want to take each of these rows. Okay, so row down. So I'm going to start with a 0. Okay, so I want to find 0% cadmium in my alley. Okay, so I want 0% metal. So I'm going to come along, and I know that this point here, okay, I'll put in the 0 and 0. Okay, so that's 0 on both sides. So that's my origin. So this is 0. Okay, that's this. Now I know the start of solidification is at 268 degrees Celsius. So if I come up, I know the degrees Celsius is on my y-axis. Okay, I'm going to find 268. Here's 200, there's 250, 260, 270, so this is going to be 268 right here. Okay, I just put in a little mark like that. The next point then I'm looking at is the end of solidification, so I'm working my way down along this row. So the next end of solidification is 140. Okay, that's 0%, so I'm going to find 0, and I'm going to move up and I'm going to find 140. Okay, so here's 100, here's 110, 20, 30, and here's 140. Okay, like that. Now, because this is a eutectic diagram, we know we can see that the end of solidification is at 140 degrees the whole way along. Okay, so that means I can come along, and I know that 140, it's 140 for the whole thing. So I'm going to find 140 over on my 100, and I can now go ahead now and draw in that line. Okay, and I'm just going to, I know I told you to do this in pencil, I'm going to do it in pen just for the example here so you can see it. Okay. Now, so all eutectic diagrams are going to have the same end of solidification, and it's known as a eutectic temperature. Now, so find the rest of my pints. So I'm going to come along, I'm going to find the next one's 10%. So I'm finding 10% of the metal in the alley. Okay, I want to find the start solidification, which is at 237. So at 10% I'm going to come up to 237, 200, 220, 210, 220, 230. Okay, and then 235. Okay, now straight away you see I'm after making a mistake on this one. Okay, so this is 268. So 268 actually should be up 50, 250, 260, 270. Okay, so this is actually 268 here. Okay, so we see the reason for doing it in pencil rather than in pen. Okay, so the next one is 20%, and that's a 205. So 20 and 205. 30, 175. 40 with 140. Okay, now this is the 40 and 40 is the special point on our eutectic diagram. It's known as our eutectic point. Okay, so it's the stage at which it goes from a solid to a liquid or liquid to solid without passing through the pasty region. Okay, so 50% is 190. Okay, so here's 190. 60% is 235. 10, 20. 70% 260, 265, sorry, 80 290, 90 310, finally 100 is 321. Okay, so now it's just a matter of joining up all these points. Okay, so we see that's kind of it's starting to come into somewhat of a little curve here, and the same here. Okay, so sometimes it can be straight lines, other times it's not. Okay, so we see that this side here is actually a straight line, so I can just draw that in like this. Okay, I'll do that in pen. Now we see if I join all these endpoints up, we see that's not going to be necessarily a straight line. Okay, so I'm going to do this freehand. Again, all this should be done freehand. You should not be using your ruler to join the points up. Okay. I'll score this in the pen. Like that. Okay, now I'm just going to draw a line up from the 100 degrees just to represent the end of the diagram. Okay, so now that's my diagram, my eutectic diagram complete. So that's part A drawn, or part 1. So drawing the equilibrium diagram using the given data. Next part is label and describe the key features of the diagram. So I'm going to go ahead and label this and describe them. So the first section going to label is this bottom section here. Okay, so this here. So everything in this section is solid. Okay. Now, the next line we're looking at is this line here. Okay, so this is known as my solidus line, and that's always going to be the end of solidification. Whatever the end of solidification line is known as my solidus line. Okay, and the region in between, so this here. Okay, so this start of solidification, anything along that line is going to be my liquidus line. Okay. Now, any of the area in between the liquidus line and the solidus line is both a mixture of solid, okay, and liquid. So it's going to be the pasty region, okay, and that's going to be this side and also this side on the eutectic diagram. Okay, everything above the liquidus line is going to be a liquid. And finally then, the main part on the eutectic diagram is this point here. Okay, so it's the point where the liquidus line meets the solidus line. Okay, and it's known as the eutectic point. Okay, it's a very special point on the eutectic diagram. Now, the next part, so that's labeling, and I want to describe the main features. Okay, so I'm just going to describe a few of them here. And the first one I'm going to look at is the eutectic point. Okay, so eutectic point. So we're saying the eutectic point is a special point where solid to liquid change occurs without passing through the pasty stage. Okay, or vice versa. Okay, or vice versa, I mean it can change from a liquid to a solid, also without passing through the pasty stage. Okay, now by describing all the key features, this is exactly what you have to do. So you're going to have to label all the key features. Okay, what I would advise is to label it to describe at least 4 different points. Okay, so just going ahead, I'm not going to write them out, but for the solid stage, it means everything in this stage of the diagram is going to be a solid. The liquid stage, everything in this stage of the diagram is going to be a liquid. In the pasty stage, everything in this stage is both a mixture of a liquid and a solid. Okay, the solidus line represents the end of solidification, and everything below the solidus line is a solid. And the liquidus line represents the start of solidification. Okay, and everything above the liquidus line is a liquid. Okay, so that's part 2 done. Now, so part 3, the final part, explain the term eutectic alley. Okay, so explain the term eutectic alley. So 1, 2. Okay, so just if I explain this, the eutectic alley is so we know solid solution alley is where both the liquid and solid is soluble in both stages of the graph. Okay, in eutectic alley, so both elements are only soluble in the liquid state of the diagram. Okay, so in solid solution alloys, both materials are soluble in both the liquid and solid state, while in the solid solution alloys, both materials are soluble in both the liquid and solid state, while in the eutectic alloys, the elements are only soluble in the liquid state and are insoluble in the solid state. Okay.